It's kind of wild how our most powerful AI models can be so brilliant one second and then just dangerously fragile the next. We're starting to hand over some really critical decisions to these systems, but they can fail in these spectacular, totally unexpected ways. So today, we're going to crack open that black box and see how a simple idea from geometry, this concept of a decision boundary, is helping scientists build a much safer, more robust AI for the future. Let's dive in.
And look, this is not science fiction. This quote is from a real investigation into a malfunctioning AI-powered morphine pump. A bug, some weird, unforeseen mix of sensor inputs, caused the pump to deliver a fatal dose. This is the reality. This is what's at stake. When AI messes up, it's not just a computer crash. It can have literal life or death consequences. So what is actually going on inside these machines?
Well, the heart of the problem is that so many of our best AI models are what we call black boxes. You feed data in one end, an answer pops out the other. But here's the kicker. Even the engineers who built the model can't fully explain the internal logic, the why behind its decision. It's like having a genius student who aces every single test, but can't show you how they got the answer.
And yeah, this cartoon pretty much nails it. We asked the AI, hey, why'd you make that call? And the response is just crickets. This lack of being able to explain itself isn't just annoying, it's a huge barrier to trust. I mean, how can we really rely on a system that can't tell us how it's thinking, especially when the stakes are so high?
Okay, so let's scale this problem up a bit. It's not just about one medical device. Imagine a world run by these mysterious algorithms. A world where your civic trust score suddenly tanks overnight, and boom, you're locked out of society. And you can't appeal it, because nobody, not a single person, can tell you what you did wrong. That's the dystopian future we're trying to avoid, with this unaccountable black box AI. But what if we could actually peek inside?
To build safer AI, researchers are looking to, of all things, geometry. They're trying to understand the invisible shapes and lines the AI is drawing inside its own virtual mind. And that brings us to this really important concept called the decision boundary. It's totally key to understanding how these things actually work. Okay, think of it this way. To tell a cat from a dog, an AI is basically drawing a line in this huge, multi-dimensional space of data. Everything on one side of that line, it gets labeled cat. Everything on the other side, dog. That line is the decision boundary. And the shape, the nature of that line is absolutely crucial for how well the AI does its job. Now check this out, because this is a really common problem. An AI can learn to draw this super complex squiggly line that perfectly separates all the cats and dogs it was trained on. But that boundary is thin, it's fragile. So a slightly weird input, maybe a weird camera angle or a dog breed it hasn't seen, can easily step over that brittle line, and poof, the model gets it wrong. So the goal then is to get the AI to draw a thick, robust boundary, just like this one. See how it creates this wider buffer zone? It's like a no man's land between the categories. And that makes the model way more stable. It's much less likely to get fooled by small changes or someone trying to trick it, because a little nudge just isn't enough to cross over into the wrong territory. And that brings us to the key metric from a big UC Berkeley paper, boundary thickness. It's a way to actually measure that buffer zone. It's not just about the one shortest path across. It's the average distance you'd expect to travel to get from a definite cat to a definite dog, right through the middle. A bigger number here means a tougher, more robust model. Simple as that. Okay, so this raises the obvious question, right? If we can measure how thick a boundary is, can we actually engineer it? Can we train our models on purpose to have these safer, thicker boundaries? Well, the latest research says absolutely yes. What's really cool is that researchers found that a lot of the techniques they were already using to make models more robust, things like regularization that penalizes complexity, or different data augmentation tricks, they all have this one thing in common. They naturally increase the boundary thickness. They were all, in their own way, pushing the model to create these safer buffer zones. One of the most powerful methods is something called mix-up training. It's a clever idea. Instead of just showing the AI a picture of a cat and then a picture of a dog, you show it a digital blend of the two, like an image that's 70% cat and 30% dog, and you tell the AI to predict that mix. This forces the model to create a much smoother and, as a result, a much thicker transition between the two categories. But the Berkeley paper didn't stop there. They took this idea and pushed it even further. They came up with a new technique called noisy mix-up. It's exactly what it sounds like. You take the already powerful mix-up method and you just add a little bit of random noise into the training process. And the result? It pushes those boundaries even thicker, creating an even more resilient model. So this all sounds great in theory, but, does it actually work in the real world? The researchers put this to the test, and honestly, the data is pretty convincing. So take a look at this chart from the paper. Along the bottom, you have boundary thickness. And going up the side, you have what's called robust accuracy. That's a measure of how well the model holds up when it's being actively attacked by inputs designed to fool it. I mean, the trend is crystal clear. As the boundary gets thicker, the model gets way, way better at defending itself. And here's the other piece of the puzzle. This chart shows that as the boundary thickness goes up, the robust accuracy gap goes down. Now, that gap is just the difference between how well the model does on data it's already seen versus brand new data. A smaller gap means the model is actually learning, not just memorizing. So, thicker boundaries help prevent that classic problem of overfitting. Now, you might be thinking, hey, isn't this just the classic idea of a margin from machine learning? But the paper shows it's actually a much better metric. The old school margin is often basically zero in these complex models and doesn't really tell you how robust something is. But boundary thickness? It's a reliable, measurable number that can clearly tell you the difference between a fragile model and a strong one. So let's bring all of this back to where we started. We've gone super deep into the abstract geometry that's happening inside an AI model. But what does it actually mean for the real world? If you're going to remember just one thing from all of this, what should it be? It's this, right here, the main conclusion from that Berkeley paper. Boundary thickness isn't just some cool academic idea. It's a practical, reliable, measurable tool. By focusing on this one geometric property, we can systematically make our AI models safer and more reliable. And at the end of the day, that's what this is all about. This research gives us a way out of that black box problem. It gives us a real, tangible lever we can pull. By intentionally engineering for thicker boundaries, we can build AI for all those high-stakes things, self-driving cars, medical devices, financial systems, that is just fundamentally safer, more predictable, and, well, more trustworthy. Being able to measure boundary thickness gives us this powerful new window into the mind of a machine. It proves that the black box isn't completely unknowable after all. And it leaves us with this really exciting question. As we develop more tools just like this one, what other fundamental secrets are just waiting inside that black box? And how are they going to help us build an even safer future with AI?